Hello everyone. Now we are going to discuss about important algorithm, gradient descent. Gradient descent is the technique which we use for most of the machine learning algorithms. It is useful to predict the model. So this model generation will be makes sensible with the help of gradient descent rather than using closed form solutions. I will explain about closed form solution and also how to use gradient descent and other algorithms as well. Now if you look into this example, when you see here, now I have imported certain libraries. So I'm having a method. So in this method I'm plotting a graph. Now here what I'm doing is I'm picking up some random values for x and then random value for y and then plotting the graph. Now you can see here we have an xy value 2D two-dimension graph. In this two-dimensional graph, what I am doing is I am using the closed form solution. So this closed form solution is basing on the training set. We will multiply the x transpose with x and then x transpose with y, and then we take the inverse of this x transpose of x and then multiply with x transpose with y, and we'll get a closed form solution like this. So this closed form solution, when you draw a graph something like this, so you get a graph like this. This red line is nothing but the model. It means if I give a value for an x 1.5, I'll get the value of 2 like this. So this, with the help this model, I'm predicting what is the value of the given input. So similarly, there is a library, stats models library, which is a open source library. We are using this OLS function and we are calling this fit model. So it when we do that, we get the model params similarly, and we when we get this model, we can do prediction basing on the input. And similarly, we for Skyline also we have a linear regression class, and we use fit method, and when we do that, we get this coefficient and the intercept. Now we are getting intercept is because we have a fit intercept equals to true. Now if you see the earlier graph, you see there is only a slope here. You can see there is only a slope. A slope is with respect to x and y. We don't have intercept. Since we don't have intercept, see it is crossing from the origin. So that's why you getting more a line like this. But if you see here, when says fit intercept is true, we are getting the intercept. Intercept, you can see the y value here. So instead of crossing from origin, it's crossed from here, from 1.1 into 1.2123 value. So this is the intercept. When you have intercept, you can see the model has fit perfectly. Now we can predict if the x value is 1.5, then value is the 2.5. so little bit more accurately you can confirm the output, predicted output. So this is about the linear regression. Now let's go to logistic regression gradient descent, and here I will be explaining little more about gradient descent algorithm. Now here I have imported the libraries. Now I have this predict function. So what I'm doing is I'm taking the coefficient, that is nothing but the slope, and then whatever the training value is there, I'm predicting the y value. Now this is the logistic regression. So logistic regression is mostly used for classifications. So if you see the linear regression, y value is something, y value is anything numerical or float value. But if you see the logistic, the output will be either 0 or 1. It's more like a yes or no. So for this you need to use the sigmoid function. There is a lot of internet information about sigmoid function and tanh function and why we use it, so that you can Google search. So only thing is, when you predict any value, so we will use the sigmoid function, so that we will get a value between 0 and 1, and with the and then return will do round that value, so that we can mention the output whether it is 0 or 1. So this is just a dummy data set you have. So I have a first column x1 and first column x2. Now here I cannot talk about x and y because we consider x as an input and y as an output. So since we have two input channels, so we say x1 and x2. There are two inputs, y which is output, that is in the last third column. So here I have just predicted some model. This coefficient is nothing but predicted model. This first and second is the x1 x2 slope with respect to x1 and x2, and the last value is with respect to the intercept. The intercept which I have said the y value which is about the origin, this part y intercept. So I just given a dummy value. Now what I do is I started little bit prediction. So when I do the prediction value, whenever I get this prediction value from sigmoid, so I use the round figure to identify whether it is 0, output is 0, or output is 1, like this. So this is how I am predicting. Now let's come to the algorithm. So our algorithm, what we are doing is we are taking this data set as it is, okay, and here is the method where I'm drawing the graph. So in this method, what I'm doing is, here I'm taking the first five rows. So if you see the first 5 rows, the output is 0, okay, and the next 5 rows, the output is 1. So what I am doing is I'm using the color coding. So first 5 outputs I am marking it as blue, and this next 5 rows I am marking it as red, which represent y equal to 1 and which represent y equal to 0. So this is the graph I am plotting. If you end up plot this graph with the help of this dummy data, this is how it looks. Now since intercept is a negative value here, now since the intercept is a negative value here, so this line is starting it is not starting from origin, it is starting from below origin. Okay, this is one of the important concept of the intercept. Now let's talk about the gradient descent. So gradient descent, what we'll do is we have some important inputs. One is training, learning rate, and number of iterations. We need number of iterations because as time pass on during this calculation of model, so what happens, it may go to infinity and it may take a very long time. For that we are restricting to few number of iterations, like 1000 iterations or 100 iterations. So we need to have this an epoch to iterate this algorithm for certain number of times. So here it is, we are doing this number of epoch. Now here we are making this assuming the some error equal to 0. So and then coefficient is origin. So we are starting coefficient origin, considering this as the model. When consider this as the model, and then we are passing this model with all the training set. So what is happening is that we get some error, because starting from the origin, obviously this is not a model. So with respect to these data points, there will be an error, and then once we get that error, we sum that error of the error squares, and then with the help of learning rate and error and predicted value, we are calculating the new coefficient value. Once we get the new coefficient value, again we are for a range of rows of training values for x1 and x2 for those columns. So we are checking for column 1 and column 2, we are updating the coefficients. I mean, this is for column 1, this is for column 2, x1 and x2 dimensions. And next here we can see we are running this method. So in this method we are passing the data set, we are passing the learning rate, and we are passing the iteration. Now you can see the learning rate is same, 0.3. In the advanced machine learning algorithms, we will change the learning rate, but for regressions we don't change the learning rate, we keep it a constant. Now you can see as the iteration comes, the error is reducing. You see after 100 iterations, so the error is reduced to 0.2, and in the end we have the slope. So the slope with respect to x1, x2 and x2 and intercept. And when we plot the graph, you can see we are able to plot the graph. Now it's easy to predict. Now if we have any data point like 1, 0.5, we can say since this is above the line, so this value is 0. Now if I say for any data point for 0.5 and 2 from around here, then I can say that the output will be 1 because this is below the line. So that's how we use the gradient descent. Now let us look into some multiple dimension examples. Now it's easy to plot a 2-dimensional graph and 3-dimensional graph, but it's not possible to draw a graph for multi dimensions. Now let us take one example. I have loaded some libraries and loading the Boston data from sklearn data set, and then I'm using this data here. You can see there are 13 dimensions and for 506 rows, and this is the description for those dimensions. And here if you see, since it's difficult to plot the graph for 13 dimensions with respect to output, so I'm just taking one of the column, that is the 13th column, last column of the x input, and with the y, and plotting the graph like this. Now earlier I mentioned about bias and non-bias. So if you don't use bias, then you will get a model passing through origin, but if you use bias, you will get it the y-intercept. So for that, what we do is, whenever you get a data like this, so we attach the last column with ones, so that with 1, so that we will get the bias or intercept value. So now you can see the x shape is changed from 50613 to 50614, because in the because we have concatenate ones, columns of ones. Now with this, what we can do is we can calculate the closed form solution. So closed form solution, what it will do is it will calculate with all 13 dimensions with intercept, bias, and then with the help of this formula we will know the model. So once we see the model, we can see the coefficients of all the slope coefficients of all the 13 dimensions, like this. Otherwise, we can use this OLS from this particular library, from stats model library, and you can also, instead of doing this this formula, closed form formula, you can use this OLS, and this also I think use gradient descent, and we'll get the coefficient of similar, almost similar values. So this is one way of looking into linear regression, it's closed form solution. Now we look into the other examples. So another examples, so what we did is, here we are loading the this is the method to load the data from CSV file, and we are declaring some methods here. So this method will convert string into float, and this method will take the data set and predict which is maximum value, this is minimum value. This is one of the very important. So whenever you get a data set, you need to know what is the maximum value and minimum value with of particular dimensions. So this will resolve the problem like a matrix metric system. For example, if you say your car is giving a mileage for 1 liter of gas to, say, let's say 10 kilometers, that makes sense. But what if I say that 1000 milliliters of gas is giving me 10 kilometers mileage? Otherwise, 10,000 meters of mileage I'm getting when I'm using 1 liter of gas. So in order to reduce this ambiguity, so we try to figure out what is the maximum and minimum value within the dimensions, so that we'll do the normalization. So for normalization, what we do is, we'll go for a particular record, and we'll using min max. So we will subtract and divide by min max, and then we'll get the normalized data, so that we can predict the models. Even earlier also, one of the videos I have covered this particular part for normalization. I explained a little bit more about it. And here, cross validation split. So sometimes what happens, whenever you're given a data, you have to split the data into 80%, 20%. 80% you use to train the data and you will get the model, and remaining 20% data you will test it and test the accuracies to see whether the machine learning algorithm is performance and the accuracy. So either you can have 80-20% or you can have 75-25%. So here you can calculate accuracy metrics. So since for you have this multiple dimensions, more than 2, more than 3 dimensions, it's difficult to do a graph. So what we'll do is, we'll measure accuracy. So based on accuracy, we will know whether the prediction is how far it is perfect. So it will compare with the actual and predict, and it will calculate the accuracy of the predicted output. So in this method we will evaluate. So in this evaluation, we'll we'll take the training set, and we'll do prediction, and out of prediction we'll take the testing set. Okay, with training set we'll get the model, and from model we'll get the we'll take the test sets, and then from test sets we'll calculate the accuracy, and from basing on this we'll update the scores. So there is a predict function. So predict is, it will take the coefficients, nothing but slope or model. So for each training model, it will calculate the predicted value, and since this is the logistic regression, it should be either 0 or 1. So for that we are using sigmoid function. So here we are using the gradient descent algorithm. So here we have number of training sets, training iteration. For each training we are iterating, and we are calculating the error. From the error we are calculating the coefficient, and once we get the first column coefficient, we are going for the next column coefficient to determine the slope. So once we get the slope, that is nothing but model. So in this method we are actually doing training testing, and we are passing the LR rate and calling the above functions. So here we are loaded the actual data here. Once we load the data here we are converting into floats, and then we are taking min max and doing normalization, and we calling this particular algorithms. Once we call the algorithms, we can see the accuracy here. So with the help of accuracy, we can tell that what is the performance of how the machine algorithm is working. So this is how the gradient descent is important and useful. And thank you very much for attending the class.